In this video, we will be servicing the lubrication system in this 2001 Ford F150. This video will include taking a sample for oil analysis, replacement of the old engine oil and old engine oil filter. It'll also include installation of an easy oil drain valve, and finally information on the oil analysis results. In order for me to take a sample of oil from my existing engine oil, I need to have an oil analysis pump, I need a length of tubing, and I need my oil analysis kit. Located on the driver's side portion of the vehicle inside the cab, we need to pull our hood release latch. This will allow us access to our engine bay, and releasing our safety latch, we can open the hood. At this point, we need to locate both our oil fill tube and our oil dipstick. Our oil fill tube is located towards the passenger side of the engine bay, and our oil dipstick is located towards the driver's side of our vehicle. The oil fill tube is fairly easy to notice because there is an oil can image on the cap, and it says SAE 5W20, which identifies the type of oil that we're going to use. The oil dipstick is a little bit more challenging to locate. It is located between the power steering fluid reservoir and the brake fluid reservoir. It is identified by a yellow ring that is connected to the dipstick. Using a rag, I'm going to remove the dipstick from the engine and wipe off the oil. I'm going to measure out a length of hose that is equal to the length of the dipstick, and then I'm going to add about an extra 6 inches of hose. Next, I'm going to line up one end of my tubing with the end of my dipstick. Lay the tubing along the length of the dipstick, and I'm going to mark the top of the dipstick. This will allow the tubing to sit inside the oil sump at the correct measurement. And then we can install our tubing into our oil pump. And at this point, I'm going to unpackage my oil analysis kit, and I'm looking for my collection container, which we can uncap and install onto our pump. After that, I can reinstall the dipstick. And I want to idle the engine and bring it up to operating temperature. This will mix up all of the oil inside of the engine and allow us to get a more accurate sample. Once the engine is up to operating temperature, we can turn it off, remove the dipstick, install our tubing into the dipstick location, and I'm going to put this all the way down to that line that I made and give it a few pumps. And I'll wait until I fill my collection container, withdraw that tubing, and reinstall the dipstick. We can then remove our sample container and cap that, and we're ready to fill out all the paperwork. Make sure you dispose of the tubing correctly. Do not reuse the tubing for another sample on a different vehicle, or you will get incorrect results. And we are ready to continue on with our oil and oil filter change procedures. To prep this vehicle for our oil and oil filter change, I have installed some Rhino ramps to help give me better access underneath the vehicle. I have wheel chocks installed behind the rear tires. I have safety stands installed underneath the vehicle in case the Rhino ramps fail. And I have put on the emergency brake. With a drip pan in place underneath the oil pan, we need to locate the oil pan drain bolt. Typically this is located directly beneath the oil fill tube on the top side of the engine. And using a 5/8 inch combination wrench, I'm going to loosen the oil drain bolt. Now we can see that there's just a little bit of oil starting to ooze out. If you're unsure whether you're taking out the oil drain bolt or the transmission drain bolt, if the fluid is very dark and black, there's a good chance that is probably the oil. If the fluid is red, that would be the transmission fluid. With your drain pans in place, we can remove the bolt. Now there's a good chance that the oil will be hot since we previously warmed up the oil to operating temperature before doing our oil analysis sampling. While we're waiting for the oil to drain out, we can locate the oil filter. This particular vehicle, the oil filter is pretty hard to locate. It's a little bit hard to get to. The oil filter is a round canister that screws onto the engine and filters out contaminants as the oil is traveling through the lubrication system. If the previous person installed the oil filter correctly, you should be able to just use your hand and unscrew the oil filter without a great deal of effort. And after removing the oil filter, you always want to double check to make sure that the rubber ring came off with the filter and it's not stuck up inside the engine. If you look just right through all of the various components on the vehicle, you can see the inlet port for our oil filter. You can double check here also to make sure that rubber ring has come off and that everything looks clean before installing the new filter. After that, we can unbox our new filter, and we want to use just a little bit of new engine oil to lubricate the rubber ring of the new filter. This will ensure a tight seal on our engine. You never want to use the old oil when you're doing this because you're essentially just rubbing dirt all over the new rubber ring then. And there's a good chance that won't seal properly. And a lot of times the installation of the new filter is actually more difficult than removal of the old filter because you can't really see what you're doing. And when installing the new oil filter, you want to install it hand tight and then just a little bit more. You shouldn't need to use a wrench or anything like that to get it on there tight. If it's too tight, you could actually distort that rubber ring and it wouldn't seal properly. At this point on a typical service, you would reinstall the oil drain plug and fill up the vehicle with oil. However, for this one, I will be installing an easy oil drain valve for this particular vehicle. This type of an oil plug has a ball valve installed into it, so the next time I drain my oil, I don't need to pull the plug out. I can just flip the switch on the ball valve and the oil will drain out. Now, when I was doing the research on these, there were a few people that had commented that it leaks around the rubber seal and it could be that they might not have installed it properly. But to prevent this from happening, I'm going to be using Permatex's Ultra Black gasket maker for surfaces that come in contact with oil. This will just provide one additional layer of protection if in fact there is a flaw in this particular part. Now you will want to read the directions with this product because there are some various setup times before installation as well as use once this is installed. After that, we can add our 6 quarts of oil. And it may be wise to double check underneath the vehicle and make sure oil isn't leaking out profusely. After that, we can cap our oil fill tube. Then we'll want to start the vehicle for about 30 seconds to get the oil flowing through the engine, and then turn it off. And once that engine oil has worked its way through the engine, we can check our levels with the dipstick. Now it may be difficult to tell the oil level because the oil is new and it is a translucent brown and kind of difficult to see. We want to make sure that our oil level is between the low and the full, ideally a little bit more towards the full. This particular one, we are sitting up near our full indicator. Typically the distance between the low dot and the full dot is 1 quart. However, we're sitting up right where we want to be at. Lastly, we can reinstall the dipstick. Double check underneath the vehicle to make sure there isn't oil profusely leaking from somewhere, and take it on a test drive. After a week or so, I received my oil analysis results. At the top of my analysis report, I have the account information, I have the component information for the particular vehicle or equipment that the analysis was conducted on, the sample information for when the sample was taken. There's some filter information, miscellaneous information, and the product information is the particular type of motor oil that this analysis was done on. Having this information allows a baseline value for what the oil should be compared to what the oil is now. For right now, I'm going to skip the comments section and move down to the actual results. Now you'll notice that there are multiple results. The NL line is a new lube sample, which is a sample that is directly out of the bottle. This is the line that I will be using as my baseline reference for comparing my current sample. Sample number 4 is the sample that was taken during this oil change service. The additional samples 1 through 3 were taken from 2015 through 2017. Moving back up to my wear metals, I want to take a look at the current wear metals that are in the oil sample compared to a new sample. Anytime there is a wear metal element identified, it would suggest that there is some type of wear that is occurring inside of the engine. The only items that indicated there were contaminants: iron, nickel, aluminum, and copper. In general, these values are not reason for concern. It was not identified by the oil analytics scientists that these were warning areas, but it is worth taking a look at the history of these particular values. Having 3 parts per million of copper is pretty insignificant, and that is pretty much in line with what I have seen in the past. The iron, nickel, and aluminum values also fall in line with what I have seen in the past. In the category of wear metals, nickel was the only one identified as having elevated levels up into the normal to abnormal range for a couple years. Given that nickel is often alloyed with iron, and I do have a small amount of iron particles in there, this value is not a concern to me at this point. We're next going to take a look at the contaminant metals and multi-source metals. The contaminant metals are elements that are an undesirable addition that somehow has found its way into the oil. The multi-source metals are metals that are coming from a variety of locations. It could be a contaminant, it could be a wear element, or it could be an additive that was placed into the oil originally. Values shown in white indicate normal conditions. Values in green are on the normal side but nearing the abnormal. Values in light orange, or kind of a yellowish color, indicate an abnormal condition. Values in dark orange constitute an abnormal condition leading to a critical condition, and values in red indicate a critical condition. Taking a look at the results, I can see that silicone falls in the same range roughly that it has been in for the past 4 years. I do not have a concern with the silicone levels. As I take a look at the sodium levels from this year, I can see that it is a bit higher than it has been. This is something I would want to watch in future reports. My potassium levels are fairly elevated. This, in conjunction with the sodium levels, gets me to wonder if there is some type of a coolant leak into the oil. Now, although it still falls within the normal range, it is something that is significantly different than the previous years. Molybdenum is a friction modifier additive, but it can also be an anti-wear coating or insert on some piston rings. That is why it falls under multi-source metals, which are metals that could be coming from different sources. My molybdenum values fall within the normal range. It appears to be fairly in line with the previous values. Manganese is an alloy used in certain steel applications, as well as a component of gasoline additives. In this particular vehicle, I do use a gasoline additive. However, I have used that same gasoline additive for the life of the vehicle, so to suddenly see a jump does issue some concern. However, in light of my iron and aluminum values being elevated, it is possible that this manganese increase is due to some type of metal wear inside of the engine. The last multi-source metal that we will take a look at is boron. Boron is a coolant additive, and it is also a lubricant oil additive. If this were to be a contamination from the cooling system, you would see the boron levels spike above the baseline levels. Given that my baseline levels are 212 parts per million, and that has been depleted down to 25 parts per million in this sample, it is clear that this particular source is from an additive that was originally in the lubricant. Boron and borates have been used since the mid-1970s as part of the additive packages to various lubricants. Nowadays, it is not uncommon to see lubricating oils and greases containing these borates. They are used as anti-wear and extreme pressure additives. Essentially, what they do is they coat the surface so it reduces the chance of metal on metal wear inside of the engine. On a molecular level inside of the engine, you have what is known as van der Waals forces. This creates an electrostatic attraction between the molecule of oil and the sidewall of your engine or whatever component that it comes in contact with. Boron, or the borates, are essential in creating this static cling type effect. And over time, those additives, boron in this case, will drop out, as we can see from the values where we started at 212 parts per million, and they have dropped out and they are down to 25 parts per million. Effectively, this indicates that the life of this oil is quickly nearing its end. Next, we will be taking a look at the additive metals that are in this oil sample. These are the components that were engineered as part of the original oil formulation. In other words, these metals should be in there if it was a part of the original manufacturer's formulation of the oil. Magnesium is an additive metal that neutralizes varnishes and sludge. In addition, it helps maintain those in a soluble state inside of the engine. Our values over the course of all of these samples indicate that the values that we have are in line. The purpose of calcium is much in the same as was the purpose of magnesium. Our values are well within the acceptable range. Phosphorus and phosphates work very similar to boron in its ability as an anti-wear and extreme pressure additive. Our values look very good. Zinc is used as an anti-wear, extreme pressure, and antioxidant additive. It is the most commonly used anti-wear additive in motor oils. It is a part of a larger additive package called ZDDP. Again, our values look just fine. I want to now jump down and take a look at the fluid properties for this motor oil sample. Taking a look at my total base number, I can see that those additives fall within the abnormal category each year pretty consistently. Generally speaking, the higher an oil's total base number, the better its ability to neutralize contaminants such as combustion byproducts and acidic materials. TBN is a measure of alkaline additives in the oil. Higher TBN oils are able to neutralize a greater amount of acidic materials, which results in improved protection against corrosive reactions and longer oil life. TBN levels decrease as the oil remains in service. When the level reaches a point where it can no longer protect against corrosion, the oil must be changed. Oils that are formulated specifically for extended drain intervals typically will have elevated TBN values to ensure proper corrosion protection for the duration of the extended interval. In general, Amsoil engineers their oil to have very high TBNs, which allows them to neutralize acidic contaminants and keep them in suspension to prevent corrosion for longer periods of time. Although my TBN values for each of the samples I've taken are in the abnormal range, this is normal as this oil is run on extended drain intervals. The oil is only changed once per year. So these values are what is remaining as far as TBN is concerned for oil that has been running in an engine for an entire year. It also indicates that after a year, the TBN is essentially depleted, thus the oil needs to be changed. Given that there is a small amount of TBN remaining, this oil could theoretically actually be run for another month or two. The next thing we'll take a look at is oxidation. Oxidation is the interaction between oxygen molecules and motor oil molecules. This is a natural occurrence that leads to chemical breakdown. Just as oxygen causes a cut apple to brown or exposed metal to rust, it breaks down the base oils and reduces the motor oil's effectiveness. Oxidation can lead to increased oil viscosity, which negatively affects energy efficiency. It can also cause the formation of harmful deposits and sludge. Lubricants for internal combustion engines are exposed to severe oxidative conditions, particularly in the upper part of the piston ring and the cylinder liner zone, where maximum temperatures can exceed 250 degrees Celsius in a passenger car engine and even over 300 degrees Celsius in a heavy-duty diesel. In these areas, there are thin oil films. We talked about this with the van der Waals forces that are exposed to blow-by gases. These blow-by gases are generated in the combustion chamber. These high temperatures and the reactive blow-by gases lead to rapid oxidation of the thin oil film. Our values for oxidation are well within the normal range and are of no concern. Nitration is of concern in engine oils, particularly natural gas engine oils. Heat can cause atmospheric nitrogen and oxygen to react, forming nitrous oxides. These nitrous oxides interact with the lubricant by creating organic nitrates or being picked up as either soluble or insoluble nitrous compounds. Nitration can cause premature thickening of the engine oil, and common causes could be inefficient exhaust of the combustion products, improper air-to-fuel ratio, low operating temperature, or even leaking piston seals. Our values from all of our samples fall within the normal range. The viscosity is the oil's resistance to flow. And as we previously talked about, there are a lot of elements that go into determining viscosity as far as why it may increase and why it may decrease with the types of contaminants in the oil. After running this oil for an entire year, we have maintained pretty good viscosity. I'm going to jump back to my comments section that I skipped earlier. These comments are thoughts that the oil analysis scientist felt were important to get across. It is first noted that the base number is moderately low, and we talked about that, how the base number started really high. The oil has been run for a year, so it has depleted that base oil value to the point where it is currently low. Next, it is noted that the potassium is at a minor level. We talked about this in conjunction with the sodium elevated levels, how that could be due to some type of a coolant leak. Here it is noted that the potassium sources could be coolant or antifreeze. Again, there could be some lubricant additives, which we kind of ruled out with the boron values. And then there's a couple other suggestions where that could be coming from. There is a note about the additive levels being different than what they should be, and it could be due to a different type of oil being topped off or something like that. This particular vehicle has not been topped off with any other lubricant. The lubricant was not misidentified. However, there was a slight formula oil change in the last year. So essentially they are saying that the values they found are a little bit different when compared to their baseline data. Regardless of the differing values, what is recorded falls in line with normal levels. There is no concern for any of the values, and I personally have no concern of the additive metal levels. Nickel was said to be at a minor level. This is something I would continue to monitor in future oil draws. The remaining comments indicate that they have noted that I did a fluid and filter change, which would correct any of these abnormal values, and that no further maintenance is required at this time. The overall report, taking into account all of this information, it is identified that this oil, after running for an entire year, is in the lower abnormal range, which means that it is nearing the end of its life. The data that we have seen reflects that, as well as the manufacturer suggests replacing the oil at the 1 year mark, which is what was done in this vehicle.